Rightio, I suspect you're probably very confused at this point if you've come straight to this video from the last video. But let's move on and hopefully give some clarity to what's going on. So previously we talked about our electron configurations, introduced the idea of subshells and orbitals, and now, and we went up to number 18. Okay, so once we hit 18, we've filled our third shell, and we come to that age-old problem where we used to have that idea of when we used to write 2, 8, 8, 2 in year 10, and we're like, well, why? Why do we put that 2 in even though the third shell can hold 18? Well, hopefully, keep listening and it will become clear. As we said before, we fill electrons in increasing energy. So the s orbital can hold, subshell has only one orbital, it holds 2 electrons. So we can put 2 here. Then we move into the 2s, it gets 2. 2p allows us to put in 6. And then 3s, and then 3p. And then hopefully you notice this guy here, it's like, hang on, I've got 3D orbitals, I should be able to move into my 3D. But what happens is, if you remember when we talked about emission spectra, we said that at higher energy levels, the energies start to converge, they get closer and closer together. Well, what happens when we get up to the third and fourth shell into the 3D subshell and the 4s subshell is that this highest level of the third shell is a little bit higher in energy than the lowest energy level of the fourth. So what this means is that electrons now, as they're filling in order, the electrons will be able to go into the fourth shell, into the s subshell, because it's a lower energy than the 3D. So because it's the s subshell, it only has an s orbital, so it can only take 2 electrons. Once it has those 2, then we just go back and we start completing our 3D subshell. So the energy difference between these two is very, very small. They're very close. And if you look at the periodic table, the transition metals that we've often not spoken about before up until now actually all have electrons going into this 3D subshell, which makes them transition metals. It gives them special chemical properties, and they all behave in particular ways because of this special electron arrangement. So when we're doing electron arrangements over 20, we need to remember that we need to fill our 4s subshell before we start putting electrons into our 3D. Okay, so this means that we apply 3 rules as we do electron configurations. We follow the Aufbau principle, which is the one that states that electrons are placed in the lowest energy level available. Okay, so the subshell with the lowest energy is filled before a subshell with the next lowest energy can be started to be filled. Orbitals can hold only 0, 1, or 2 electrons, no more. And then Hund's rule is that says orbitals of the same subshell are the lowest energy is obtained when the number of electrons of the same spin is maximized. This means if I had, say, my 3p, where I've got 3 orbitals, if I was putting 3 electrons into my 3p, they actually go 1 per orbital, okay, before we come back. So we keep them without a pair as much as possible, and then we come back and pair them. I like to refer to this as the metro rule. Okay, if you think about hopping on a tram, people generally go 1 per seat. If we've got seats in a tram, people will generally go 1 per seat until the tram is full, and only then do they come back and tend to sit next to other people if they're traveling alone. Okay, so we don't tend to like to sit on the same seat. Electrons are the same. They like to sit in their own orbital unless there is no more space, and then they pair up. So this is what we refer to as an orbital diagram, or sometimes an Aufbau diagram. Okay, so this shows the orbitals labeled 1s, 2s, 2p, 3s in order of energy. So we can see here helium is in period 1, it has only 1 shell. Both electrons go into the 1s, 1 up, 1 down. Lithium has 3. We're in the second period now, so we have the first shell and the second shell. So we pair up the first shell and then move into the second shell. Boron moves along. By the time we get to nitrogen, now we have 2 in our first shell, 2 in the first subshell, which are paired up. Now we've got 3, so 1 into each orbital in order to keep them unpaired. This is another way of showing Aufbau diagrams. In this case, we have energy going up the vertical scale and the boxes are just stacked in increasing energy. 1 box for each orbital. So essentially what it comes down to is we just follow the rules. We put 1 electron per orbital until there's no more orbitals in that energy level, come back and double them up. So I want you to have a bit of practice and write the electron configurations for these compounds here, and we'll go through them in class. Okay, so while I said we just follow the rules, it is chemistry, and chemistry is one of those sciences that loves to have exceptions to its rules. So we've just told you the rules, and now let's look at some exceptions. So things get a little bit funny when we hit our 4s3d, so that weird kind of close energy. Because they're so close in energy, there's very little difference between the energy in these orbitals. So we get situations where it's actually a little bit more stable to have partially half filled rather than partially filled. We see this when we have chromium. Okay, so where chromium sits, we have 24 electrons. So this symbology here means that the electron configuration is the same up until argon, okay, which would be 1s2, 2s2, 2p6, 3s2, 3p6. So that's what that little condensed electron configuration means, that I am exactly the same up until argon, and then it's 4s2, 3d4 would be what we normally predict. What happens though is chromium's actually more stable, and things always aim for more stability. If we actually go to 4s1, 3d5, what this means is that we end up with 1 in the 4s1, and then we have the 5 d orbitals, and because remember we said that they prefer to be unpaired if they can be, we end up with them all being unpaired, which makes for greater stability. The other one that we see as an exception is copper. Now we're at 29. Okay, so we're at 29. So instead of being 4s2, 3d9, we get greater stability if we make the S1 on its own and pair up everything in the 3D. So these are our 2 exceptions to the Aufbau rule. Looking at them according to our Aufbau diagrams and our condensed notation. So everything that we've talked about at the moment has said that we put electrons in from the lowest energy to the highest energy. That means that everything is in the ground state, which is the lowest possible energy state, with all the electrons in the lowest possible orbitals and subshells. So when something is excited, when we talked about before giving it energy, it becomes excited and promotes to a higher energy level. What happens is the electrons will move up in the possible orbitals. So we will see an orbital, an excited sodium atom here, 1s2, 2s2, 2p6, okay, and instead of 3s1, we see that it's given the configuration here 3p1, which means our s1 electron has actually jumped to a higher energy level in a p orbital, and we can see it's excited. In order to identify if something is excited, we just need to pay attention to see if there is an electron in a higher orbital than it should be and something's empty below it. Okay, and then we can show that here. We can see that this electron here has been promoted up into a higher energy level from 2s1 to 2p3. Have a go at doing these questions, and we will do a lot of practice on this in class. Just want to get the ideas of the theory down and make sure that you've got your notes and those definitions tied up, and I'll see you in class.